So let's talk a little bit about the idea of space resistance or geometric resistance. So we have this relationship for the surface. So for a surface from I to j, we say q dot I to j is equal to Fij ai sigma ti to the fourth minus Fji aj sigma tj to the fourth. That's an energy balance, net radiation exchange between surface I and j, or surface I to j. If we look at this, actually, let's use our idea of reciprocity. So reciprocity, we said ai Fij is equal to aj Fji. So using that idea, let's substitute that into the second view factor, the second term up there. And we end up with an equation where we can pull out that ai Fij times sigma. And we end up with here, Qij is equal to ai Fij times sigma times ti to the fourth minus tj fourth. All right. Actually, there's another way we can write this. So we can also write this as ai Fij. Remember, sigma t to the fourth is actually just our emissive power, right? That term E that we talked about last time. So we can write this as an emissive power difference, this being EI minus EJ. Right? If we look at this, again, we have kind of this rate equation, right? It's Q dot times the view factor times area times a potential. In this case, the potential is, well, T to the fourth, but it's also, in terms of emissive power, it's just the difference between the emissive powers of the surfaces. So this we could also write as an equation with a resistance, right? You could introduce this resistance. And the resistance would be, if you write it as resistance, Qij is going to be this should be EBI minus EBJ. These are black body emissive powers divided by some resistance, which we call Rij. Previously, I guess, in 364, we'd call this Rgij. So we could do that here just to differentiate. So it's Rgij. And the idea is that this resistance is different from the conduction resistance or convection. It has different units. It's kind of a slightly different idea. So it's a geometric resistance instead of kind of a traditional resistance. But this is what we have, and this geometric resistance is just equal to this view factor times the area. So it'd be Rgij. It's going to be equal to 1 over ai Fij, which is also equal to 1 over aj Fji. Right. So what is this resistance telling us? It's telling us we have two emissive black body emissive powers for two surfaces. They are separated by space, by this view factor. That resistance is telling us how hard is it for radiation to get through space from one surface to another surface. Right? That view factor tells us how hard it is for radiation to find that one surface. So it is kind of like this space resistance or geometric resistance. So we can use this, right? Again, the units on this are actually, what, 1 over meter squared? Right? So it's different units from other resistances. You don't want to put these in the same network as other resistances without doing some things to it first. But so we can use this in the same way that we use other resistances to write rate equations based on the rate of heat transfer between these two surfaces and write out networks and things like that. We'll actually do that. So let's kind of conceptualize what we have here. So we have, obviously, the easiest way to write this would be EBI. And then we have this resistance here to EBJ, and we'll call this Rgij, right? So it's the same idea. And then we have heat flow, as usual, Q dot from I to J. So let's think about how we would use a resistance like this when we are evaluating or analyzing these radiation problems. So let's take again, let's say we've got some triangular three-surface enclosure. Let's call this 1, this one 2, this one 3. So if I'm going to characterize this using resistance network, I have to think about all the surfaces and how they can all interact with each other. I would start by looking at surface 1. So surface 1 can definitely exchange with surface 2. Surface 1 can also exchange with surface 3. Right? 3 can go to 1, 3 can go to 2, and vice versa, right? So you have this basically a 3-node resistance network that we can draw that characterizes this problem. So we could do that down here. Let me just. Okay, so down here, let's draw a resistance network for this. So let's say we have 3 nodes, 1, 2, 3. So up here we have, let's call this node 1, this is node 2, this is node 3. So I'm going to draw resistances between each of these nodes. Right? These are going to be my geometric or space resistances between each of these nodes. So this is going to be a network that I'm going to use to characterize the heat flow based on the resistances in this problem. So, all right, so at 1, what is the effective kind of potential associated with 1? Normally, if we're writing a heat transfer resistance problem like this, that potential is the temperature. Here we have T to the 4th, right? So it's not quite the same thing. So we actually want to write these in terms of our black body emissive power. So this is EB of 1. That's our potential at 1. What's our potential at 2? Well, it's also EB2. Our potential at 3 is EB3. Right? We could have heat flow coming in and out of each of these nodes. So we could have, here we could have heat flow coming into 1. Here we could have heat flow coming in 2. Here we could have heat flow coming into 3. Right? I'm writing, so we want to be careful to point out here, I'm writing Q.1, Q.2, Q.3 as opposed to what's the heat flow between nodes, right? So heat flow between nodes here would be Q.1, 2. Okay, so there's a double index there on the 1 going between 2 specific nodes. Q.1 could also go to 3, so we'd call this Q.1, 3. And it then must be true that Q.12 and Q.13 have to add up to Q.1. Right? Those all have to add up. Let's see. So we would then, we could also label these. So this resistance up here would be what the resistance between 1 and 2. So this would be RG 1 to 2. This would be RG 2 to 3. Here, 2 to 3. This would be RG 1 to 3. Right, we could also write it RG 3 to 1 or the other way around. But, right, so this is going to be our network. So we can now use this network to write equations to relate the potentials and the heat flows and the resistances. Okay. Yeah, so we'll go through an example, I think, in a couple of minutes here. We'll actually do something like this. I think you probably can imagine how this will go. You write, let's say we want to write Q dot from 1 to 3. We'd write that rate equation using the resistances. If you wanted to write, let's say you had, this would be an example. So let's say that this surface over here is actually adiabatic, right? I could write a rate equation that goes from 1 to 3, but I'd have to include Q dot 1, 2, and I'd also have to include heat flow that kind of goes around the corner here. And so go all the way from 1 to 3 via that whole network, but then I have to include both those space resistances in my network when I'm writing it. Right? Yeah. Oh, this should, up here, this should be 1 to 2, right? Is that what you're saying? Yep, I did it backwards. Thank you. So 1, 3, this is 1. Thank you. So your Q dot 1 to 3 total is going to be the Q dot from 1 to 3 directly, the one I circled, and then the one that's going via that sort of circuit, right? That other circuit. Okay. If this over here, if Q dot 2 is not 0, right? If that's not adiabatic, then you can't write it entirely like that. We have to write a balance on each node and then have a system of equations that we solve. So maybe that's a good segue for, okay, this is 3 surfaces. We can draw a 3-surface network. Can you imagine how a 4-surface network would work, or a 5-surface network, right? Right, you start to see that, okay, every surface can see its other counterparts. You're going to have these crisscrossing resistances, and it actually is not that helpful to draw a resistance network for those types of problems. But for those types of problems, let's say we have an N surface. So this is going to be an N surface resistance network. So how do you actually approach these problems? Because in reality, there are very few situations where you have 3 surfaces, usually N surfaces. 3 surfaces is helpful for us to like conceptually understand what's going on. N surfaces is really usually what happens. So what you need to do for N surfaces is, let's think about, let's take one surface over here. Let's start with surface I. We're going to say this has potential EBI. Right, coming into surface I, let's say I have Q dot I. So there's N surfaces that this particular node can exchange heat with. So if I was to draw a network, that might look something like, well, I could go over here to surface R. So we're going from Ri to surface 1. And so this would be EB1. I could also, in parallel, go to Ri2 with potential EB2, and so on, down to Ri to N with potential EBN. Right, so this is going to be for one surface to every other surface. I could then draw an equivalent network for every other surface that I have. So I have N of these resistance networks that I have to deal with. Right? I can write an equation for this one surface. I can write the equation for heat transfer to other surfaces is Q dot I, right? The total heat coming in. Surface I is going to be somehow related to every single interaction with every other surface. So to account for that, I want to say Q dot I is going to be right, AI times the view factor from I to J, but actually AI is going to be common among all those things. So let's just write out AI first. So AI sigma, and then I have the sum from J equals 1 to N of Fij Ti to the 4th minus Tj to the 4th, or kind of more appropriately, as I've written it over here, it would be AI times the sum J equals 1 to N of Fij, the emissive power difference of EBI minus EBJ, right? And this is going to be for I equals 1 to N. So, okay, so I write this equation, and let's say you can establish the view factors for each of the surfaces, right, which we will do in some examples. You establish the view factor for each of the surfaces, you get by reciprocity the counterparts going back, or enclosure rule, or whatever, to set up this whole matrix of view factors. And then you can write one equation, so this is one equation for one surface, right? You have one equation summing up all the contributions for all the other surfaces. This is one equation for one surface. I then have to repeat this, right? We're going to repeat this for each surface. Each surface J, or sorry, each surface I. Let me make sure I wrote this right. So for I equals 1. Okay, so this is going to be, we're repeating this for each surface I, and then we have N equations, right? We have N equations in this system that describe an energy balance on each surface. All right. What you'll notice, though, is we actually have we have the areas, we have the view factors. We don't know what heat transfer Q dot. The N equations are going to give us the emissive powers, but we're not going to have the Q dots. Or let's say we have the Q dots, we're not going to have the emissive powers. So we actually need two N equations for this. And this system gives us N equations. So then the next thing we need to do is we're going to need to specify for every single node some what we call boundary condition about that node. So we have, say, N equations, but need 2N equations. So we specify boundary conditions for each surface. What are those boundary conditions? Well, it can be anything that pins down that surface. So let's say you're given in a problem a Q dot for a surface, or you say I have a heater, you're putting this amount of power into that surface. In that surface I that you have that heater, you'd specify Q dot, and then you could use that to calculate the emissive power, right? You could equivalently, you could specify a temperature and say my surface is at this temperature. Use temperature to compute emissive black body emissive power, and that gives you another equation, right? So you can be, depending on the situation, you can be creative, I'd say, or fit it as needed to your system of equations, but you do need to have N boundary conditions that you provide in addition to this energy balance for each surface. Okay. So that's kind of the method. This is actually something that I haven't set up the homework for next week, but I think this is probably what we'll focus on for the homework, something like this. So probably worth your time to think about it a little bit. Yeah. Yes. So we are right now assuming everything that's emitted or everything that's incident on a surface is absorbed, right? The full power that could be emitted is being emitted. So this is for black surfaces. We will get to gray surfaces and talk about that. So then you have reflection, you have interactions. So. Okay, so in the last few minutes here, let's go through an example of how to do this. The process is a little tricky sometimes, so let's kind of walk through it.